Good afternoon and welcome to today's Microwaves and RF webinar, Designing Expendable SIGINT and Electronic Warfare RF Front-End Technology, and it's sponsored by Mercury Systems. I'm David Maliniak, Executive Editor of Microwaves and RF with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Just type them into the Q&A/tech support box to the left on your screen or on the left rail, where the bubble with the question mark appears. As a reminder, for a better view of today's event, you can click in the upper right corner of the presentation of the media player windows to expand them. And to refer a colleague to today's discussion, share it on social media or access event resources by clicking the icons on the left side rail of your screen. Also, please be aware that today's session is being recorded and will be available on the Microwaves and RF website within the next 24 hours. You'll be notified by email when that archive is available. Now I'd like to introduce our presenter for today. Darren Hinsey is Senior Principal Accounts Manager for Mercury Systems' MMIC line of business. With over 25 years in the electronics and semiconductor industries, Darren has introduced new technologies in computing and RF to customers around the world. Darren holds degrees in electronics engineer technology and applied sciences. So let me turn it over to Darren. Darren, the floor is yours.
All right. Thank you very much, David. Hey, it's glad to be with everybody this morning. Again, just a little bit about me. I work with the design team here in our Atlanta office. This is the MMIC group from Mercury. So our focus is to design solutions for largely broadband RF applications. So as the market has moved over the past several years, we've noticed some changes and some accelerations in specific areas. It's being driven by a number of low-cost requirements for expendables and drones and some of these many things that have been in the news over the past several years. It's certainly impacted our business, so we're grateful for some time to come and show what we're doing to address these new challenges and how we see how we're pushing our technology to address these new needs from our marketplace. So we're going to talk specifically about expendables and other very low-cost needs in SIGINT and EW today. So for an agenda, the changing demands in EW and SIGINT with the emergence of expendables has pushed us down I would say, an extreme swap C path. Swap has been around for a long time, but it's getting extreme, and we're going to talk about what we're doing to address that. There are a couple of design strategies, fixed or single purpose, and also flexible design strategies. Do I want to design something? Does it make sense to design one very specific, very low-cost thing that I use once, and then that goes with that design, and I rip up the page and start again? Or does it make sense to design a block that solves a lot of different problems that I can reuse? And we'll talk about those different design strategies and how we engage with each of them. And then we're going to talk about how we design our MMICs to solve these problems for our modules and for our customers. First of all, amplifiers that aren't just amplifiers, using the amplification stage to do more than just amplification and solve problems. Flexible filter solutions, so using a single part with programmability so the filter response can move around with some digital or other type of input. Integrating multiple functions into MMICs, how we do that, not just using a single part, not just as one single block, but to cover many. And then how we can MCM things together, how we can take multiple die, package them together to save space, to improve RF performance, and for other reasons. Finally, we'll go into some of our standard RF tuner modules that we offer, and then we'll finalize with some applications and what we see happening in this space. So a little bit of background on where we come from. Our group was founded by a group of engineers, former Boeing engineers, who were largely software-defined radio engineers. So they come from the super heterodyne tuner space. And they wanted to go out and design better tinker toys or better building blocks for these broadband radios. There's a lot of focus on narrowband types of things, but when you're talking about frequencies that go from DC to 18 gigahertz and above, there's unique challenges to those very broadband systems, and they wanted to design mimics that were better building blocks for that specific need, that specific requirement. So we come from that heterodyne space. However, with the emergence of direct RF, the filtering technology, particularly the tunable filtering technology, has relevance into direct RF. So as we talk about this, there's that heterodyne versus direct RF choice, and direct RF is coming. But to maintain a very low-cost final solution, there's still a good argument between what's less expensive, a little bit more work on the front end, versus how much can I afford to do with both money and power with just crunching bits. So right now we're still in kind of a sweet spot where heterodyne makes some sense up front, but direct RF is certainly coming. Our roots also come from a largely multi-channel background. So before 2022, let's say, a lot of the applications that we saw were multi-channel receive, usually 2- and 4-channel applications, coherent, for direction finding and SIGINT type applications, maybe with a transmit channel to address things, but largely there was a large disparity between the number of receive channels versus the number of transmit channels. And again, that was largely driven by direction finding type applications. We've also done a lot of work in mobile spectrum analysis. So the companies that are providing the FCC with equipment to make sure that we're not transmitting over cell phone frequencies and things like that. And of course, we've done a lot of work with the 3-letter agencies as well. Since 2022, there's been a bit of a shift in what we see predominant in our market space. We've shifted away from multi-channel RX to a lot of times we see just a single channel TX RX pair. So that's changed a little bit the mix of what we do and how we do it. It's going to have a lot. It will have a lot of effect on our tuner module roadmap for sure. But it's certainly changed the way the type of questions our customers ask and what we're designing our mimics to do going forward. The other thing that is different is the role that particularly that low-cost bullet is playing. When you're designing a few tens of things to go to be the EW front for a large military asset or for a city or something like that, cost is less of a concern. It's certainly much different if you're going to be throwing things over hills or over the horizon. You don't expect them to return. And you want to be able to do that a number of times and without worrying about cost of use. So we are certainly seeing a cost and size. And when I say cost, it isn't just the cost of components. It's a system cost. It's power. It's cost to manufacture. It's ability to manufacture many things. So all of those things go into a system cost calculation, and we're certainly seeing a lot of pressure in that direction, a lot more than we have in the past. Now, another request that we're getting is for modular design or future-proofing. We need to be able to address emerging frequencies of interest that may pop up where they weren't expected, and we need to be able to address those in a short period of time. I can't have a front end that's deployed in the field that's not capable of addressing a signal that may be popping up that I wasn't aware of yesterday. I need to be able to rapidly configure hardware to address new realities. And then the final thing is, with all the new types of things that are being designed and all the new demands for resources, how do we take care of all these new demands for resources with what is a very limited resource space? Let's face it, design engineers are not, there's not one every stone's throw. It's a rare breed, and it's an expensive breed, and particularly good ones need to be leveraged properly so we can solve the most problems with the least amount of engineering effort. So how do we solve these how do we starting with something that needs to be large and needs to be low cost and manufacturable, how do we start taking that problem apart? Well, we start at the very, very low end. And one of the unique things about our group is we can solve problems down at the MMIC level. Again, as a company that it was founded by software-defined radio designers, being able to build the building block that will solve problems is an important way that we can bring solutions to the market. And a lot of the MMICs that you see for sale on our website are direct results of us solving a particular problem at a tuner level. And we figure if it's a problem for us, it's a problem for the marketplace. So we try and solve as many problems as we can at that stage. Also, once a problem is solved at the MMIC level, it's eminently reproducible and low cost. Die cost and packaging die is much lower cost than trying to solder parts down and build things on a circuit board level. So if I can solve problems at the miniature level, the space savings and power savings is much greater than solving it at a higher level. Next, we put multiple things into a package. So instead of just having one part soldered down that does one thing, if I can solder down one package that does many things, it's saving a lot of space. Saving, and particularly if it's already tested, it's a section of my board I don't have to worry about. Everything works. I know that block is sound, and I can focus my attention elsewhere. Finally, portability. Because we are able to do these things and we can make choices, we can make portable designs. One of the things that we do is we talk to many customers and hear input from many locations. We will aggregate what we hear into a very small single module that tries to address as many of those concerns as possible. And then for that specific module, we can go redesign the steps to get to that module. So we can make these very small general purpose modules and release those to the marketplace. And then reproducibility. Once we do that, we do manufacture for scale, so we can build all of these things up here in the thousands and tens of thousands, and at the MMIC level, the hundreds of thousands of units level. So we have something that's scalable, and we can scale up and produce quickly. All right, let's jump into some specifics. So I mentioned overachieving amplifiers that do more than just amplify. Well, let's start with the 1102. One of the things that we are known for is building amplifiers that have a very flat gain curve. So to start with, when you're looking at a very broad frequency range, not inducing any additional problems in the space by an amplifier that isn't flat is important. So first, we're going to do no harm by introducing a flat amplifier across the spectrum. Next, we'll add some programmability. So in some cases, I may want to be able to remove an amplification stage. So in some applications, so if my front end needs it, I can have it. If I'm in another application that doesn't need it, I can bypass it. So if a single switch, I can bypass the amplifier. And the last thing, something unique that we've done is we've done these aggressively positively sloped, or what we call equalizing amplifiers. And what we designed these to do is to correct for those high frequency losses that occur elsewhere in the system. So I know I'm going to have higher frequency losses in switches due to my board, et cetera. If I can get a gain stage in and compensate for those losses, I can pull some attenuators and some equalizers off of my board. Because those have been very popular, we've introduced a family of those so that you can kind of pick your correction. The 110 is the most aggressively positively sloped. You put that down. If that's a little bit more of an overshoot, well, we've got some pin-for-pin compatible parts that can be scaled down to fit the exact need of the board. You change the part once, you go to manufacturer, and it's good to go. We've also expanded the frequency range. So that's one direction we're being pushed, is that frequency range that only goes one way. So our frequency ranges are always getting higher. One of the key technologies that allowed us to make things smaller and was technology that was developed by our founders was the filter technology. Oh, do you have audio? Sorry, do you have audio? We lost audio?
We lose Darren?
Okay, I'm back. Can you hear me now?
Yes, sir.
Okay, all right. Sorry about that. Let's see. Where did you lose me? About has it been fairly recently? Am I still here?
Yeah, we're still good. You're free to go.
All right.
Just for a second.
All right. Okay. All right. Thank you. Okay. Filter technology. Sorry about that. Techie stuff. Filter technology. So being able to have a flexible filter and being able to put filters that move around in frequency is a key part of being able to design a flexible solution that's going to be adaptable and small. So we provide a number of options in a flexible filter space. So we do switched filter banks. So again, just a number of filters with a switch fabric. We allow tunability. So we can tune that filter down to a very narrow space. One of those options is for digitally tunable. The other is for analog tunable. And then we also do some notch filters. And just briefly where you may choose each one. Because switch filter banks, they have kind of the highest Q and the lowest insertion loss. Those tend to be kind of your front end. Those are what are going to do my initial filtering. Digitally tunable filters, where they fit in is they have the next highest Q. Because they're digital, they act like something digital. There's steps. There's a corners that we pick that are inherent to the part, and you can step through and create those filter selections that are within the digital step framework. So higher Q, but some limited to the steps that are inherent to the part. The analog tunables offer the most flexibility, but the Qs are a little lower, and of course, then you've got the analog voltages that you have to deal with. So kind of those different considerations as you consider which tunable filter to use. We also do some analog notch filters. I'm not going to cover those much here, but we do some tunable notches as well. All right, for switch filter banks. So switch filter banks we make in a small QFN packages. So this happens to be a 2 to 18 front end. We make them in a couple of configurations. This one is a constant 2 gig. It's a constant 2 gig space. So if you are designing this for, if you needed, say, a constant 2 gig IBW final tune application, this might be something that you could use for that constant open aperture with some overlap. We also make these in sub-octave as well. So you kind of pick which type. We make many different flavors of these, but they all look pretty much the same with an input, a switch fabric, your choice of filter ranges, and a switch fabric coming out. The tunables really start with that same type of configuration, but then they add the tunability. So you'll have some digital signals going in to select a frequency range, but then the digital signals will also select a knee. So you can select a high and a low knee, and that will form your bandpass. And with the digitals, for ours, they are parallel digital inputs. There are others on the market. Some of them will use a SPI input as well. So you've got other solutions that use that way, but we use just standard parallel inputs. So you don't have to worry about any RF signals. You can feed those up through long distances, and it will not. You don't have to worry about RF. You can scale down your RF and not have to worry about that running through your system. The analogs work very much the same way, where you'll have a digital selection, so you'll select which frequency band you want, and then within that frequency band, you can narrow down the frequency pass band. A couple of things about limitations. So there are some limitations to this technology that are important. One is, as you can see, it's particularly obvious on this analog filter. If you look at that very first curve, you can see that as it's wide, the insertion loss is up around -5, but as it gets narrower and narrower, it's down around -8. At about 20% of center frequency, this becomes a no-pass filter instead of a band-pass filter. So we do want to make sure that there is a limitation there as to how narrow the frequency range can be with all of the tunables. With analog, if it's about 20%, the digitals we can get to about 15%, but you're not going to get something like 3 to 5% out of this type of technology. There is a limitation there. The other limitation is in switching speed. There is a switching and tuning time due to the capacitance. It is usually in the microsecond or under range, but there is definitely a switching speed and tuning time that you have to manage when you're doing analog. Sorry, I was on the wrong slide. Let me just reiterate that again. You can see the insertion loss on the low end is about -5 up there, and on the low end it's about -8. So that's what I'm referring to. As you get narrower and narrower, your insertion loss gets higher. So at about 20% of center frequency, that becomes a no-pass filter. All righty. So multifunction mimics. One of the things that we're able to do is we're able to put many things into a single mimic. When we first started releasing our tuner modules, we were asked how were we able to make things so small? Well, one of the reasons we were able to do that is to put many things into a small package. This particular device is not on our website. It soon will be. But as you can see, this is a complete front-end pre-selector. It has a tunable low frequency side. So this is on the 2 to 7 band. It's a tunable. That's the mark of the arrows there. It's a tunable filters with an amplification stage, and then fixed filters above with switch fabric. So, and this is in a small little 6mm package. So in one small package, we're able to make an amplified pre-selecting front end that contains, about 18, what would be 18 solder down devices if we were to put them down one by one. So that's one way we're able to make things very small. And now that it's been designed and it's in the mimic range, it's very reproducible. We can produce a lot of the chips, and it's very scalable. Another thing, so we're also able to do multi-chip modules. So where it doesn't make sense to make a module or a single chip, there does have to be a reason to do that. The design is expensive. So if the design's too expensive, but it makes sense to put things in a single package, a half step is to take the pre-designed mimics and put them in a single MCM. And the space savings doing this can be substantial. So this is a fairly typical or standard RF front end. This happens to be a 2 to 18 front end with a limiter, a tunable filter stage, and some amplifiers. You can kind of get an idea of the size of everything in the package. As you go through the coupler, the limiter, the filter is the big square in there. The two amplifiers are smaller, and then the one miscellaneous thing is just some filtering for the control lines that go in. We can put these all together in a package, and what was a 30mm square, we can reduce to 12. There is some cost involved with this, but even for things that are hundreds of units, this type of thing can make sense because now you have something that's small. It'll save you some space. You'll know that you're getting a chain that is already tested and works the way it should, and you can focus attention elsewhere. With one solder down piece, you've got an entire block of your solution completed. By the way, we can do this. This is a fairly complex example of what we do. I'd say more of what we do tends to be 2 to 3 things instead of 5. And sometimes it's a chain, and sometimes it's a filter bank that, maybe you buy a filter bank that does 2 to 18, and I want to add, maybe in a bypass path, I want to add something that takes care of 100 megahertz to the 2 gigahertz range. So I can do something that's wider as well. All right. The tuner modules. One of the unique things that we're able to do, because we can design things from the Tinker Toy stage, is assemble them together into small tuner modules. And we really started releasing these tuner modules back in 2019. And as we started to do that, these are very small, simple to use. They're meant to be an entire solution between the antenna and the ADC. They're controlled by a SPI signal. Send it a SPI command. The tuner goes to that frequency, goes to the frequency it's commanded to, tunes, and gives you the instantaneous bandwidth, the rated instantaneous bandwidth at the IF frequency out the back end. Some customers, for some applications, find an LNA on the front is useful. Some will do some additional filtering on the back end for anti-aliasing, and some customers just use them as is between the antenna and the ADC. These have been extraordinarily popular modules for us. Again, because we're able to do what we can, solving problems with mimics, we have some advantages building things to make them very small and optimized for size and cost. The 9018 and 30 followed. They were introduced in about 2022, and this is where some things started to change. That's where we introduced our first transmit unit. And when we designed these, we anticipated the use to be more in line with what our historic use cases were, which was customer would come, they would have a direction finding type application. So there would be 2 or 4 receive channels. These are capable of being coherent and doing direction finding. And then maybe they would add a transmit channel in to address a signal that they wanted to do some type of interdiction or addressing. But the primary use would be about 2 or 4 to 1. That has changed radically over the past couple of years, and in fact, we now have more customers adopting transmit units to pair with some of our previous generation transmit or receive units, and so that's changed a little bit the way that we've gone forward. The other thing we did is as we've gotten market feedback with these first channels. These were designed specifically to make them as small and as space efficient as possible for many different applications. But as we've been driven in different directions, a few things have happened. So one is the demand for wider apertures is always there. So our latest module is a 9029. It's a 2 gigahertz instantaneous bandwidth, but it's narrow construction. As we've kind of looked at form factors and where the adoption of where the modules go, they do get adopted into a number of places, by the way. When I talk about flexibility, the modules that we produce, those single modules, go into everything from balloons to aircraft to trucks to boats to rack-mounted 3U VPX type systems. So they do get adopted everywhere, and because we have some manufacturing scale, that's one of the advantages of the modules is we're now at scale manufacturing with them. But as we've done that and looked at the form factors that we're being adopted into, the narrow channel construction has several advantages. For the rack mount, the 3U or 1U VPX cards have a lot of width or have a lot of length and don't have a lot of width, so that narrower channel construction lends to additional channels or more channels that we can fit onto a 3U VPX card. The other thing for that expendable or reusable, or excuse me, non-reusable application or drone application, a lot of those tend to be in a very small tube. So, or that type of form factor, that type of external structure. So again, having something small and narrow, having that type of channel structure is advantageous. So as we go forward, you'll see more of our offerings aligned to a narrow, longer channel type construction. So that's one way that we're being driven, and we are being driven wider. Today, I'd say largely the market that we see is still in the 1 gig. The 1 gig IBW is probably the most common adoption today. 2 gig IBW I think it's still a little early for those. We do see some adoptions. We are developing mimics for the 4 gig IBW generation that we anticipate to come later. And I think we're still kind of debating whether, where does that direct RF intercept point come? because that direct digital world, those direct digital solutions do become less expensive. The cost and power of those only go one way; it goes down. So as there is going to be an intercept point, we think there will be a 4 gig, but not sure that there will be one after that. But all that being said, we are developing mimics, and this is what drives a lot of our mimic creation. So as you see, going back to the tunable filters, if you're in a space where your design requires different band breaks or a different set of filters than what you see on our website or what you see available in the general market, a discussion with us is worthwhile, because we are constantly developing filters with different corners, and we have lots of things in our design box that has not been released to the market. So if you have some questions about something, or something looks like it should belong in the marketplace or should be an emerging thing in the market, it's not quite there yet, please contact us, because if it doesn't exist in our toy box already, there's a good chance we're either working on it, or we would love to talk to you about doing it, because we probably should be doing it if it's a problem for you. I'll just give you a recent example. Sitting down with a customer that needed a 1x8 switch. They talked about the application basically. You know what? That's a great idea. We think that product should be on the market, and you'll see in the next month or two that product emerge on the market space. That was a specific request from a customer. No NRE involved in that. We just thought it was a good thing that the market should see, so we developed the part. And we're glad to have those types of discussions with customers at any time. We will engage in customs as well if you do need something specific, but not everything has to be, hey, you pay us NRE and you own it. We do entertain building things that have market relevance. The other direction our tuners are being pushed is higher frequency. So this is our 9035A tuner module. So this expands. This is meant to work with our 0 to 18 frequency tuner modules. It works in very much the same way, where you send it as a command, it tunes to those frequencies and produces a signal at the IF. But being driven higher in frequency is a constant. This is at 44 gigahertz today. We are, the roadmap for this particular product is going to be up into the 50s. It's probably a year from now is where that's milestoning out. But this particular product is, despite the roadmap, this is a fixed product from us. It is adopted into programs, and it will have a long-term supply chain. I should say that about all the modules. Our modules, once we release them as standard products, they do get adopted into programs with very long production cycles. So we do build these with the intent of a 20-year support cycle. Fortunately for us, because we're also the MMIC manufacturer, we control a lot of the BOM and what the MMICs are, so we won't be EOLing our own parts. We do rely on some very common synthesizers and mixers and FPGA, but controlling most of the BOM is a good way to ensure that we don't EOL our own system. Next, the other way we're being driven is to put more channels into a smaller space. Can I get coherent channels, more coherent channels into something that's smaller, so I can make it mobile and make it lighter? So you will see more multi-channel things emerge from us. The 9036 is our first 4-channel board. At this point, again, because of those customer requests, I believe I've made every possible iteration of this is either in design or been released. So this is a 4-receive channel. I have a 2-up, 2-down version that'll be on the website later this year, and a 3-down, 1-up version that's also in design. So we'll see every iteration of the tuner modules, of this particular tuner module going forward. Again, as a summary on the module approach, because we have some specific advantages being a designer of mimics and being able to solve problems at the mimic level, we can partner with customers, with end users, to create a platform at this level or at a chipset level, buying something that's not quite a module but has all the chips relevant, but you want to put it down on your own board. That's another way that we can engage and solve problems. If it's less expensive for us to supply that level of a solution, we can also partner with you and design something specific. If you need if you look at something that's on the website, you need a slightly different IF, or if you need a slightly different configuration, we can certainly talk to you about how we can specifically design things. So we do engage in NRE to full production design. To give an idea of how much how long each one of those things take and how much is involved, at the mimic level. So if you want a specific standard amplification stage, something's not on the market, or you have a very specific frequency range you need to work with that can't be disclosed, we can talk about that, and with an NRE process, we can build a mimic in about 8 months to a year, just kind of depending on the complexity. The MCMs, if you have a chain of our devices that you just need built into a single package, that's actually very easy for us to do. We can discuss a chain with you, put together an MCM and get you an MCM, a completed, ready to produce MCM in about 5 to 6 months. And a tuner module is about a year-long design cycle, assuming we're starting from scratch, if we're not just changing an IF or doing some type of a small modification to an existing module. But we certainly can do that. So finally, how do we bring all these things together? There we go. Okay. How do we bring all these things together to create these lower cost systems? How do we do that? Well, the design decision you make up front, whether it's I'm going to design something specific because what I have is high volume, I need to be very efficient with every single step, we can engage with you at the mimic level, help you solve those problems at that level so that your single purpose design is as efficient as it can be and as reproducible as it can be. As you step up in flexibility, we can engage with you as it makes sense in each step up the chain, whether it's programmability and flexibility of filters and amplifier stages, or whether it's complete tuner modules. And we can provide a level of manufacturability, and particularly in the case of modules where these things generally aren't in volume production, we can provide a solution that is in volume production, that is tested and ready to go as a solution, as an end solution for you. And again, finally, as we're pushing forward to direct RF, we do see just filter modules and front-end modules becoming more common as well. So we don't need to do something complex. We can also do something very simple and partner with you to make something very powerful in just a few parts that accomplishes a complete front end in a very few devices. With that, that's the end of my presentation. Thank you for participating today. I'll be happy to field any questions.
Okay, great presentation, Darren. Thank you very much. Yeah, a few of the attendees have submitted questions, so we'll jump into those in a moment. As a reminder, if you would like to submit a question now, just type it into that question window on the side of your screen and hit the submit button. And also, if you would, please stay until the end of the presentation to complete the exit survey, which will pop up on your screen. You can preview those questions now by clicking the exit survey icon on the left side rail. Okay, let's just jump into some of those questions now. You talked quite a bit, Darren, about direct RF. It's a really interesting technology, and the viewer's wondering how direct RF changes the design discussion.
Certainly. So, again, we come from that superhet space, and we are in a space that at least currently the super heterodyne receiver with a lighter digitization stage seems to be the lowest cost place to go for many applications. But that's not always the case. And it's certainly not going to be the case as those direct digitizing solutions get less and less expensive. So there is certainly an argument now as to at the end application of what's better. We do see that the direct RF is coming and it is going to have a future, but because we can make those super heterodyne solutions so inexpensive, there's still a role for those today.
Okay. Another viewer says that he doesn't see what he needs on the market. So to that end, does Mercury's MMIC business entertain custom requests?
Yes, we'll entertain custom requests at any level of your design. So if the tuner module doesn't quite fit, we'll do a tuner module. If the MMIC doesn't quite fit, particularly on that level, there's a lot of things that we can design for you if you have very specific needs, or a lot of times we have things just under the hood. A specific example: we had a customer that had a part go end of life from another supplier just as they were going to go to production on a very important military product. Which those of you who live in that space know that sometimes those can be years-long design cycles, and you hit an EOL before you even reach first production. Fortunately, one of our customer interface resources was sitting with that engineer, talking to them about the solution. They called us and said, "Hey, we don't see something on your website, but do you have something that does X, Y, and Z?" As it turned out, we had that exact part already done in our Tinker Toy box. We hadn't released it because we didn't see a specific market for it. But as it turned out, we were able to supply that specific need, that specific customer with a need, without even having to go through a custom design, and that customer was able to go forward and meet their production with that part that was already done.
Cool. Yeah, those defense projects, they can go on for years. That's for sure.
Yeah.
What's the yield on MMICs in general, and can you quote what's been the largest volume for a single design that you've done?
Certainly. So the yield on our MMICs, I would say, of course, that varies on the complexity, but it's well north of 90% on all of them. So we are able to build things again. That's one of the reasons why they're low cost. The production is very repeatable, and we can run it out, and we get very high yields on our MMIC parts. The highest volumes to date we can supply numbers up into the 30,000-ish in a few months time frame. So it's that level of production that we can hit. So we could do hundreds of thousands over the course of a year.
Okay.
That depends a little bit on what the MMIC is. Obviously, the smaller the die, the better. But the things we've done 30,000 tend to be we've done some of our more complex filter designs. We've supplied tens of thousands of those in short periods of time.
All right, that's impressive. Why wouldn't a fixed RF design using very low cost components be better than going the MMIC route?
Okay, so there is an open debate with that, right? Is the specific thing high enough volume, and is there enough space in the engineering cost that designing to one thing is the best thing to do? That's true. There's a case for that. But more and more with design engineering resources being limited, if we can do one thing and if we can design one thing that can solve multiple problems, we don't run into engineering resource problems.
Okay. EMI performance is always important to the folks that use products like yours. How is the EMI performance for Mercury's receiver modules?
Certainly. So these are meant to be used in EW spaces. So when you're looking at something like, well, I'm going to make an assumption that we're talking about some type of a jam or some type of something that's trying to interdict the signal. There is an input limit. Limiters can be used up front to help that, but there is a very large out-of-band discrimination to each one of the modules, and you can kind of look as you select it on the data sheets at the performance of each of the selection levels. So we do design for very wide out-of-band rejection. That's one of the things that we are taking into account because this is the world we do live in.
Okay. If a designer wanted to cover multiple separated frequency bands, is it better to use a hardware switch or a pre-selector filter in your architecture? And what would be the advantages for one over the other?
Okay, good question. So there are different cases for each. So the pre-selector, obviously, it's small. It's got because it's a MMIC. There are power handling capabilities, and I've made the choices of where those breaks are in each of the selections. If you need something different, particularly if you have, I'm sorry. If you have power handling. Oh no, that's okay. If you have power handling issues, the MMIC may not be able to handle the power that you need to handle at that switch level. You know, there is a case to be made that look, when you do something all in MMIC, there's a cost to that. There's a cost to the silicon. If you're just using a hardware switch and some very cheap filters, with the components themselves can be lower cost, but again, you have to look at what is the system impact of that. It's going to be larger. There's going to be more components to put down, and then you've got something else to test versus something that's been mass produced and works coming out of the box.
Okay. A viewer's asking whether Mercury's MMIC business would ever be made into an internal design facility that doesn't market products outside.
Okay, good question. So we were purchased by Mercury. This was, to be honest, what my concern was when I was part of the Atlanta Micro team when we were purchased, and I thought, one of the things that because of Mercury's, we've solved some EOL problems for them, but no, we are the fastest growing entity within the Mercury Corporation, and Mercury does not want to limit our exposure to just what they are doing. We remain a very fast-growing entity within the company. Okay. So no, I don't see that as a remote possibility.
Cool, that's good news.
Mm-hmm.
Are OpenVPX receiver cards available with a digital Vita interface?
Very good question. Not today, but they are coming. One of the things that Mercury does do OpenVPX type tuner card solutions. They haven't done one that's integrated our tuners yet that looks like that, but they're certainly working on it. So a good question, and yeah, stay tuned for that.
Okay. We'll take just a moment. Let me just. Okay. We have another question in. What's the path to a low loss, high power, like in the 10-watt range, front end filter, either tunable or switched, for broadband systems at the antenna?
Okay, so that's a little bit outside of where I live, but I'll talk about it just briefly. So if you're talking about the path to higher power, generally we live in the gas world. I'll kind of answer this in the part that where we live and kind of leave you to answer the rest of the question I'm not going to answer. So most of our technology is gas-based, so we tend to live in that 2 watts and below space. So what we do see, though, for that higher front end is the mimic that hang on, maybe I'll skip back here real quick and just pull this up just briefly. This MCM that we did, that limiter on the front end is to limit power input and get us down to a more manageable power input. So to get rid of a jam or some other local high power emitter, for example. By the way, in this particular example, that happens to be a Corvo part. We do not make limiters. So just to go back, we can bring in a custom piece of die or something from another manufacturer if it makes sense when we do one of these parts. So
Okay.
good question. Sorry, I didn't completely answer that, but that's what we see as a limiter then that goes to our technology.
Okay. Let me just take a moment to remind everyone that you should stay until the end of the presentation. There's going to be an exit survey that'll pop up. If you want to preview the questions now, you can do that on the icon on the side rail. Okay, one more question we have here.
Go ahead.
How transportable are the Mimic designs from your business, from foundry to foundry, if one should close, and what would the delay be if you were transferring a design?
Good question. So this is a particular concern for how do we manage our long-term business, because Mimic designs are not portable, as I think the users of that product are well aware. When an acquisition happens or a process becomes unavailable, the design can be transported to a new foundry or a new process, but the results aren't exactly the same. We would face that same challenge. How are we managing that? Well, so we do die bank. We have a good long-term supplier that is used by, I would say, every large Mimic supplier in the market space.
Mm-hmm.
We do use die bank and things like that. We're putting those types of things in place to mitigate against supply chain disruptions. And we do cross. We are bringing up additional foundry capability as well. Again, one of the advantages we have in producing end products with Mimics is for the end products, we can try and solve those problems someplace else. But certainly an amplifier that is designed on one process that moves to another process, because that process becomes unavailable, that's a type of thing that we manage by, one, ensuring that we're with a good long-term partner with processes that have long life cycles, and two, managing risk by die banking key parts for customers. So again,
Okay.
Very good question.
Okay, great. And with that, I'm afraid we're out of time for today. For those questions we didn't have time to get to, we'll get back to those questioners via email. And that concludes today's presentation. On behalf of Microwaves and RF, I'd like to thank Darren for his presentation today, Mercury for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of the day and watch for that exit survey.